Hi, this is Dr. Jivikas Paul. In this session, we are going to discuss about deflections of beams using different methods. So we'll see how the slopes and deflection in beams are calculated using various methods like double integration method or Michaelis method, moment area method, conjugate beam method, and strain energy method. And for each method, we have different cases, different beams like simply supported beam, cantilever beam, and overhanging beam. For each method, we'll see. And for different load combinations, like load may be point load, uniform distributed load, uniformly varying load, point moment, or combination of all these loads. So in this session, in this unit 1, we'll study the how to calculate the slope and deflections for beams using various methods. Right, we know that the loads will come on beams, and beam from it will be loads will be transferred to columns and then to footings. Now, coming to beam, it is a member that can be comprised of a number of materials including concrete, steel, wood, aluminum, etc. to withstand loads typically applied laterally to the beam axis. Like if it is a beam, load will be applied laterally to the beam, and beam consists of concrete, steel, etc. Then types of beams, as we already know: simply supported beam, cantilever beam, overhanging beam, continuous beam, fixed beam, propped cantilever beam, etc. Types of supports: roller support, pin support, fixed support. We know that for your roller support, only one reaction is there. For pinned or hinged support, two reactions, vertical and horizontal. For fixed support, three reactions, vertical, horizontal, as well as moment reaction will be there. Vertical reaction, that means there is no movement in the vertical direction. There is no movement of support in vertical and horizontal direction. There is no movement in vertical, horizontal direction. No movement is also there. No movement is there. Next, basic assumptions. Deflections are very small and stresses are within the elastic limit. These are the very basic assumptions. Then coming to deflection. See, you can see this beam here. Before loading, beam is straight. When the load is applied, W, this is simply supported beam we have taken. After the load, this is the case. That means the beam will deflect, bend in this way. And this portion is called as deflection, Y. This is called as elastic curve. This is after loading, before loading. So it is a vertical distance of the beam measured before and after loading. Vertical distance. It is denoted by Y. Deflection at support is always 0. At supports, the deflection will be 0 for the simply supported beam. Next, slope. It is angle in radians. Angle in radians measured between the tangent to the elastic curve and the original axis of the beam. See, this is the original axis of the beam. This is the tangent drawn to the elastic curve. So this angle between these two lines is theta. Here also axis of the beam and tangent at this support B. This is angle theta B, theta A. This is deflection theta A, theta A. So here if you observe, deflection is 0 for this case. At A, deflection is 0. Here slope is 0 at the center, but slope is there at A and B. Because at this point there is no slope. So angle is 0 here. Next, coming to boundary conditions. For simply supported beam, if we see, this is simply supported beam deflection curve. See the load and the deflection. So if the load is at center, deflection will be maximum here, Y max. Okay. So at A and B, theta is max. So at A and B, the boundary conditions are for simply supported beam. At A, theta is maximum. Is there any deflection? There is no deflection. Y is 0. Here also theta is maximum, theta B, Y is 0. But at center, slope is 0 and deflection is maximum. For cantilever beam case, see here, if you see here, this is cantilever beam deflection curve, and deflection, maximum deflection is at B, and here there is no deflection and no slope. If you see here at A, Y equal to 0, theta equal to 0, because it is fixed support, there is no slope, no deflection also. But here there is slope as well as deflection also. See, angle between the axis of the beam and tangent drawn. This is theta B. This is maximum deflection. These are the boundary conditions for simply supported beam and cantilever beam. Next, if a beam carries UDL or point load, the beam will deflect from the original position. Yes, when it carries load, it will deflect from the original position. Due to the loads acting on the beam, it will be subjected to bending moment. So due to the loads, it is subjected to bending moment. The radius of curvature of the deflected beam is given by, so this R, see here, this is the original beam, this is the deflected shape. If I extend this arc, it will be a circle. It will be a circle with center O. So O is the radius, OB is also the radius R. Y is the deflected shape. Here we have completed considered simply supported case. So the radius r is given by ei by m. How? We know that from bending equation m by equal to e by r. From there we will get r equal to ei by m. The radius of curvature r equal to ei by m will be constant if the beam is subjected to constant bending moment. Then the beam will bend into a circular arc. So if the beam is subjected to constant bending moment, then the beam will bend into a circular arc. Deflection of a beam subjected to uniform bending moment. So we'll see a derivation here, a deflection equation for deflection and slope for a beam subjected to uniform bending moment. So first of all, a beam AB of length L is subjected to uniform bending moment, hence it will bend into a arc. So first of all, we have taken a beam AB, simply supported case. AB is the original, ACB is the actual length, original position. Next, the initial position of the beam is ACB, whereas deflected position of the beam is AC-B. So due to the load, what happened? It is deflected in this way. So this is AC-. So AC-B is the deflected position of the beam. This is deflection, this is slope, everything we know. This is center. I have extended this arc. Center is O, OA is R, OB is R. Okay. Now what I did is I have drawn a line in this way, straight line, and I have noted this as D. Okay, so now A, D, B, O, C, C dash, right? Length is L, length of the beam is L. So R is radius of curvature of deflected beam, Y is the deflection of beam at center, I is the moment of inertia of beam section, Young's modulus of beam material, theta is the slope of the beam. So from geometric of the circle, we know that AC into CB is equal to DC into CC dash. Same thing I have written here. But AC is L by 2, CB is L by 2, AC is L by 2 because total is L, L by 2, L by 2. DC dash minus CC dash. See here, DC I can write DC dash minus CC dash. Okay, so DC dash minus CC dash. But DC dash is the diameter, D. DC dash is the diameter of the circle. So L square by 4 equal to D minus Y into Y. CC dash is Y, deflection. Okay. So from here I have written this one. So D is nothing but 2 times R, 2 radius. Therefore this we get this. So in practical Y square is very small, therefore Y square can be neglected. So I am making this Y square as 0. So L square by 4 equal to 2RY, Y equal to L square by 8R. But R is EI by M from here. So I am substituting the same thing here. Then we will get, if I substitute, I will get Y equal to ML square by 8EI. This is the deflection equation, Y equal to ML square by 8EI. Now how to find the slope equation? I am taking the triangle AOC. If you observe the triangle AOC from the figure, from this figure AOC, this is theta. If this is theta, this will also become theta. How? See, this is theta, this is 90 minus theta, this is 90 degrees, this is theta. Therefore, if it is 90 minus theta, it is 90, it will become theta because inside triangle, sum of inside triangle will be should become 180 degrees. So 90 minus theta plus 90, 90 plus 90, 180 degrees. So it is also theta. So from here sin theta equal to opposite by hypotenuse. So sin theta equal to opposite AC by hypotenuse AO. So L by 2 by R. So theta equal to L by 2R. So I am substituting R equal to EI by M. So theta equal to ML by 2EI. This is the slope equation for the deflected beam. So the deflection equation is ML square by 8EI and slope equation is ML by 2EI.